Okay, so our question today is from Lexy, and the question is, what is the Boötes Void, and how did it come to exist? Right. So here's the short version of that answer. So the Boötes Void is so called because it's near the constellation of Boötes, and it's basically an area of space where there are far fewer galaxies than we expect there to be. And we think that this is caused by various fluctuations just after the Big Bang that have evolved over 13.86 billion years through the age of the universe to leave a much lower density of material than the areas around it. So now, here's the long version of the answer to Lexy's question. So as we said before, the Boötes Void, but you can call it Booties if you want.
I prefer Booties.
You prefer Booties?
But whatever. I think Boötes is more accurate.
It's more accurate, yes. So the Boötes Void, as we said, is an area of the universe which is observed in the constellation of Boötes, and it's basically a dark patch on the sky. Now, of course, my natural inclination as an astronomer, and as a stellar astronomer at that, I'm out of my depth in cosmology, but my natural inclination was to go, oh, it's just it's just stuff getting in the way of stars behind it. It's just dust, it's just gas. So when I first heard about it, that was my immediate response when you first mentioned it. But it's actually a real thing. It's actually an area of space where there's much less density of material there than there is in the areas around it. And in fact, I think if you look, there's about 60 galaxies in the entire area. I think it's 300 million light years across? Something like that. It's quite massive. It's the most massive void that we know of in the universe. So yeah, there's 60 galaxies in there, and in the same area or the same volume, you would expect to see about 2,000. So just to give you an idea of how far spread those are, if you placed the Milky Way, our galaxy, into the middle of the Boötes Void, we wouldn't have known there were other galaxies in the universe until about the 1960s. That's how far separated they are. So we're actually, ourselves, we're in a filament. We're in a cluster of galaxies. So if you look at the scales, we are in the Milky Way, obviously, and the Milky Way is part of the Virgo supercluster, the Virgo cluster of galaxies, which are basically nearby galaxies to us. And then if you go up to larger scales, you end up in the Laniakea supercluster, which is massive. I don't remember off the top of my head how big it is, but it's about 100,000 galaxies are contained within this supercluster. And much in the same way that supercluster contains a load of galaxies, contains our nearby galaxies, our nearby universe, the Boötes Void contains the opposite of that. It contains the nearby nothingness for all of these galaxies. So the natural question, and I think what Lexy's question then goes on to, is why does that void, this super void, the biggest super void that we know of, exist? So to do that, we kind of have to look back at the Big Bang. We have to look back at the instant after the Big Bang. So 10 to the minus 32-ish seconds after the Big Bang, the universe is still quite small, and it's at this scale that you end up with these quantum fluctuations in space-time that happen all around us now. But the universe is much bigger. But these quantum fluctuations kind of change the density. They disturb the density of the universe, right? And so when you get to larger scales, still the quantum fluctuations aren't a problem anymore because you've got much bigger. But you end up with interactions between the really simple matter in the universe and the light that is kind of trapped in the very early universe before it could travel. Basically, you end up with these interactions causing oscillations in the matter in the universe, and that's going on right up until around 380,000 years after the Big Bang, when something called the recombination happens. and the universe basically starts forming your hydrogen, and all of the stuff that's stopping the light from traveling, all of these ionized plasma, suddenly isn't a problem, and the mean free path of the light, how far the photon can travel before it gets scattered, is suddenly larger than the observable universe. So the light can propagate. And so if you've ever seen the cosmic microwave background that was, I believe it was observed by the Wilkinson Microwave Anisotropy Probe, right? WMAP, is that right? If you've ever seen this iconic image of the cosmic microwave background, then what you're actually seeing is the light that was then able to propagate as this happened. So you're seeing like a fingerprint. You're seeing like the state of the early universe as that was happening. And what this tells us is really interesting things. So it tells us obviously that the universe, roughly speaking, is the same in every direction. It tells us that no matter which way we look, the universe looks the same.
Despite the fact that WMAP map does show fluctuations on it.
Yeah.
But I guess those fluctuations are tiny.
Those fluctuations are tiny, yeah. They're on the order of 10 parts per million. So they're minute fluctuations. But the point is that those fluctuations probably led to the large-scale structures in the universe that we see today. And they were caused by overdensities and underdensities caused by the quantum effects of the early universe and the oscillations between the interacting plasma and photons in before recombination happened. So essentially, if you take that snapshot and evolve it forward 13.86 billion years throughout the history of the universe, you end up with the large-scale structures that we see today. So you end up with these filaments and globs of material on these massive scales, on these supercluster scales, that you then can form galaxies and stars out of. And as a natural result of the fact that you have kind of bits that are higher density, you also have the bits of the universe that are lower density, where you have voids, where you have much less material. It's like a massive sponge, basically. It's kind of got a filamentary and blobs of structure propagating through the universe.
I've got another question, though, leading on from this. So, considering that this void appears to have nothing in it, but of course we know that space is three-dimensional, right? So that this filament is probably, I don't know. Sorry, this void is probably spherical-ish.
Yeah.
So there must really be stuff on the other side of it, right? But we can't see that, I guess.
Yeah. So there is stuff on the other side of it. There's probably stuff.
Yeah, there can't be some cylinder going out into the edge of the universe, the nothingness.
No, there is stuff on the other side of it, yeah. But in the same way that if you look out into other galaxies, you can't see the stars. You can't see the individual stars really, just due to resolution or due to how faint they are in comparison to the galaxy itself. Or even if you look nearby, things like brown dwarfs, if you look at them in the optical, these things glow in the infrared. You can't really see them in the optical. So in just that same way, these objects that are further away appear to us to be quite faint. Because, of course, the light coming from these things falls off in intensity as 1 over the distance squared. So for every distance that we move that it is away from us, the brightness of the light that it's giving off that we see is going off as squared distance. So of course, as you go further and further away, you start seeing less and less of the light that's coming from this thing. So of course, there are things on the other side of the void. There are things on the other side of the Boötes Void, but it's more difficult to see them because to us they appear fainter. This brings me to mind of the Hubble Deep Field. So do you know about the Hubble Deep Field?
Yeah, so it was this really lovely kind of photo, basically, of the early universe in a tiny, tiny patch of sky, right? And recently, I guess they did a new version in the same
have
patch
they?
of sky. Is that right? Or not that recently?
Right.
They took an original one and they took a deep, ultra deep field.
Yeah,
Is that right?
I think so. Yeah, that sounds about right. Sounds about right. We're going to find out it was in the Boötes Void now, aren't we? That's going to how this is going to go. So essentially, what they did for the Hubble Deep Field and the Ultra Deep Field, apparently, is they took the Hubble Space Telescope and they pointed it at one particular patch of sky for many, many, many days worth of observing time. And what that gives you is the incredibly powerful image of even the parts of the sky that appear to be empty to us, the ones that we can look at even with moderately good telescopes, and they appear to be fairly empty, fairly devoid of things. If you look at them for long enough, suddenly all of these amazing things that are further away, that appear really faint to us, start showing up. And so Hubble, I think it stared at the same patch of sky for tens of days, just to build up this really deep image. And by deep, we just mean how faint it goes, right? So the depth of what you're seeing is just how far away you can see, what level, what's the faintest brightness you can see. So when we say the Hubble Deep Field, we of course mean it's seeing to really faint things because it's had long enough to build up these small amounts of light coming from all these galaxies. Okay, so hopefully, Lexy, that answers your question. And if you have any more questions, then please feel free to get in touch either by email or Twitter, yeah? And that information should hopefully be on the screen right now. And look forward to the next questions for Ask an Astrophysicist or Ask a Physicist. And thanks for watching.